and thank you for joining us in our symposium on cognitive aspects of trust in human AI teams. My name is Ismail-Tsaous. I'm from the Bavarian Research Institute for Digital Transformation, which is part of the Bavarian Academy of the Sciences and Humanities. And this symposium is part of our project Ethical Implications of Human AI Teams, which is a joint project of the University of Hohenheim and the BIT, and we do research on ethically compliant design of human AI interaction, and in particular we focus on the effects of different contexts, explainability methods, and interactivity options on trust and performance in human AI teams. Okay, this is our today's agenda, and we have 4 talks. And I wanted to give a very short introduction, but I will skip that since we lost some time. No? Okay, well, I will try to cut it really short. Okay, so let's start because it's something to prepare the upcoming talks. Okay, we have an increasing number of applications that use artificial intelligence, and currently the machine learning models are very predominant, and these systems are very performant in specific tasks like image classification or natural language processing, so tasks where a huge amount of data is required or that can't be easily programmed because they are too complex. And to be able to handle these amounts of data, the models have to operate stochastically. That means they have quite complex structures with many parameters, and that makes these boxes to black boxes. And black box means we have some kind of input, in this case an image of a butterfly, and then something happens and we get a result, and in this case it is correctly classified as an insect, but we don't know how the system came to this result. So this wouldn't be a problem if these systems were always right, but they simply generalize over a huge amount of data, and so they rely on approximation and heuristics, and that makes them prone to error and false confidence. So in this example, we see that this model is very convinced that this stop sign is a clock, and there are other examples. So for example, here with a large language model, where it is quite evident that the generalization is purely statistical. It's not semantic. So we have this, it's sometimes called Tom Cruise problem. I don't know if you've heard of this, but if we ask who Tom Cruise's mother is, it answers correctly, but it does not work the other way. So we have a phenomenon that models trained on A is B cannot automatically infer that B is A. And this was with GPT-4, I think. So it's not a very old model. And these kind of errors are errors that humans wouldn't usually make, so they can decrease trust because they are very obvious also. Okay, so do people trust AI systems? It's not that easy to answer the questions. Fortunately, there was a study from the University of Melbourne and KPMG on a large scale with more than 48,000 people across 47 countries. And I want to present some findings, and especially about AI use at work. And as you can see, 53% of the employees report that they trust using AI tools for work purposes, and 58% use them regularly, but that's not too much. But 67% of the people that use them report a positive effect on their work efficiency. That means they're not too bad, but there are also results that can raise some concern. 72% of the surveyed people report that they have at least once put less effort into their work, knowing that they can rely on AI. 66% have relied on AI without evaluating the information, and 55% have already made mistakes due to AI, and some of them have this experienced often or very often. It's quite interesting. So we can see here that some people rely on these systems without checking the results. And there's another aspect I want to point out, and it's that reported trust, if you ask people if they trust the system, can differ from the behavioral trust in the sense that they rely on the system, but maybe are not aware of that. Okay. So to sum this up, we have trust in human AI teams, and we want people to trust systems in a way that it matches the abilities of the systems. That means we don't want them to undertrust these systems because they wouldn't use them, and we want this over-reliance, which makes them delegate tasks and do not detect, they do not detect errors or biases, and that's especially important in fields with, in high-stakes fields like medicine, where human oversight is necessary and also legally prescribed. And one way to get the right amount of trust can be explainable AI. And the idea is that the model is explained in a way that people can understand how it works and also decide if they want to trust it. And this sounds quite good, but unfortunately the relationship between explanations, trust, and performance is also quite complex. And this brings us to our first speaker. So I will shortly introduce all speakers so we can, we have to wait, I'm sorry, because it will be better for our time management. So the first talk is about effect of different types of explanations. It will be held by Ute Schmid, who's head of the Cognitive Systems Group at the University of Bamberg. She's also a member of the board of directors of the BIT and member of the Bavarian AI Council. After that, we will hear another talk about interpretability, and this will be given by Johannes Hirnkrantz, who is head of the Institute of Application-Oriented Knowledge Processing at the University of Linz. He's also associated with the LIT Artificial Intelligence Lab, and he will talk about interpretability of machine learning models and human preferences in explanations. And after that, we will hear Fritz Becker, who will show insights from a psychological perspective, and he will talk about the influence of users' expertise and the perception, the influence of the perception of the system's trustworthiness. And our final talk will be about decision-making contexts and the different types of over and of trust that I've introduced already, over and under reliance in different decision-making contexts and ethical issues concerning trust. And he is Senior Research Associate at the Chair of Business and Social Ethics at the University of Hohenheim. He holds 2 doctorates, or I don't know, but he finished 2 doctorates, and that's it. So please welcome our first speaker, Ute Schmid.
So I will talk about explain to understand and explain to revise. So I think both understanding explanations and with the explanation at least partially understanding the underlying computation of an output of a machine learned model and the ability to interact in a meaningful way with an AI system for interactive machine learning are both important cognitive requirements for human AI teaming. And Eda already mentioned the European Union AI Act, and in the context of preparing this regulation, there was a high-level expert group which identified 7 requirements for trustworthy AI, and I will, of course, now not go into all of them, but just point out 3 of them. So on the top, you see that the most important requirement considered by the European Union expert group is human agency and oversight. And I would agree completely here that this, when we want to meaningfully work with AI systems in work context especially, then human agency and oversight is crucial, because in the end it is us humans who are the decision makers and problem solvers, right? And the second bullet which I want to point out is the one which is labeled transparency. And in this context, explainable AI plays a major role. There are other aspects of transparency, but XAI is one of them. And finally, but I will not talk about this today, but we work a little bit on that also in my group, is that technical robustness and safety also can be supported when you do neurosymbolic or hybrid systems, in the sense that you combine machine learning approaches in a meaningful way with classical symbolic methods of AI. So in the context of the project Ethyde, which Eda mentioned, where we all work together on, we discussed in an interdisciplinary team the concepts of trust and trustworthiness. And many people, especially from philosophy, but partially also from psychology, are very skeptical whether the EU named this right when they said this is trustworthiness. And trust and trustworthiness typically are components in human-human interaction, with lots of research in psychology about that. But for the time being, we take these labels, trustworthiness and trust, because they are introduced. Nevertheless, we should be a little bit critical about the use of these words. So in general, humans bring with them, from their personality, a basic inclination to trust or distrust, right? And as a part of this, humans have overall tendency to be more trustful or not distrustful concerning technical systems in general. And in the next step, people are more or less inclined to trust AI as a very global concept, right? So this is a kind of generalized trust, which is mostly influenced by attitudes, but also by experience and knowledge. Yeah? On the other hand, what we look at, so this is the human perspective. From the AI system perspective, we have these general trustworthiness requirements where the European Union would hope, and this is what regulation is now also starting to be set up to do, that you get checklists, that you get for, let's say, some current large language model, a list with check marks how trustworthy this system is along these 7 criteria, for instance, right? So we call this normative trust. So in the rest of the talk, and I think also in the other talks, we focus on something else, which we call evidence-based trust. Yeah? So what we are interested in is a specific person working with a very specific machine learned model, let's say in medical diagnostics, let's say to diagnose skin cancer, one specific system, how they can be supported in calibrating their trust in a way that for every output of the system, they spend a sufficient and adequate amount of time to reflect and check this output. Of course, if you would check everything in completely deep detail, what Edda showed from the questionnaire, from the survey, would no longer be valid, because then we would not really get much more efficient with working with AI. But to calibrate trust, to know when to look in more detail and when to say, okay, I go along with the system decision, is what we want to support. So now first glance into XAI. Edda also already introduced this. I want to remind you that XAI as a research discipline in its own right raised in 2016 where David Gunning gave a talk at the ICHCAI, and he used this slide. Yeah? And in this slide, he argued 2016, there were no generative AI models around. This was the big time of deep learning, especially CNNs, for instance. He said, well, typically a standard machine learned model just gives you the output cat. But what we would like to have would be something like explanation. And he gave an example, which is a very human-style, multi-model explanation, like verbal descriptions of semantic features, for it has fur, and also visual prototypes, because obviously perceptual knowledge is mostly implicit knowledge, so you give prototypical images of how cat ears look like, right? So this was the beginning, but what then happened was LIME and other systems you might also know about. LIME was one of the first XAI approaches. The paper from Ribeiro is cited over 6,000 times, and many, many people are using LIME. Not so much nowadays anymore, because there are questions about faithfulness of LIME explanations, which I will come to in a minute. So the basic idea of LIME is a really cool one and a very pragmatic one. So you have your learned model, and this is a black box model, like a CNN. And you don't have to intervene in any way with the learned model, but what you do is you perturb a specific input image. Yeah? Meaning, for instance, if this left was your original input, you create, or LIME creates, many, let's say 10,000 perturbed examples, perturbed instances, and perturbation means that you mask specific parts of the input. Yeah, by different strategies. And then you only look locally in the decision boundary of your model for these perturbed images and basically count for which of these images the classification is still tree frog, for which not. And then you aggregate over the input, which is pixel information, which pixels contribute most for this specific CNN trained with specific data to the classification decision. This is a tree frog, and in this case, it would be the head of the tree frog. So this is LIME, and these type of explanation methods are called relevance methods or feature relevance methods. And there is also a very well-known approach from a German group, the HHI in Berlin. They have the layer-wise relevance propagation approach, which is also feature highlighting. And what I want to show you here is that a really very helpful application of these feature relevance methods is for the model developers themselves to check whether the model has overfitted. So I don't know all of you here, so I don't know of your specific backgrounds. I will spend a minute to explain and hope that I don't bore my AI colleagues too much with that. So overfitting means that a model has adapted its parameters to irrelevant features which correlate, have a spurious correlation with the output classes, right? And in this case, maybe you have a sample of images where for all the images where horses are on, you have this copyright mark somewhere in the image. And since machine learning is mostly optimization, and it's much easier to optimize to this letter detection task, the system learned whenever there is a copyright notice, say there is a horse. Yeah? And you might not notice this when you calculate your F1 score or whatever metrics you are using for your test data, but you can note this when you use an XAI method like LRP or LIME and see, oh, the model overfitted to something irrelevant. And this is called clever Hans models. The models appear to have high performance, but they don't have. Okay. So I already mentioned that LIME has been shown to be not very faithful. This is an important problem when we talk about the helpfulness of explanations, because when I want to use XAI methods for users to calibrate their trust, it should better be the case that the explanations really relate to the things the model is doing. Yeah? And so this is a crucial question, and nowadays when you publish methods for XAI, you have to do ablation studies to demonstrate that your new method is faithful. Yeah? Okay, so here a very early work from my team, 2019, where we could show that LIME is not faithful because the way how you compose these superpixels to perturb your images, so which pixels together you mask, depending on the method, you get completely different types of explanation. So it's not very robust. When XAI became more prominent in discussions, there were critical voices like this one in Science, beware of explanations from AI in healthcare. But this was focused on these type of feature highlighting explanations because often you found papers where people said, well, look, I have this cool new XAI method, and look, I asked people afterwards with one rating scale, do you trust the system? And the people said yes, so cool, XAI helps to make AI more trustworthy, and obviously this is not a very plausible and differentiated way to think about this. So explainability is definitely not useful per se. Explanations need to be tailored to the question, whom do I explain what for what information need? Yeah? This might depend on how to explain. I already gave you one example for explaining for model developers, overfitting and also bias detection, which Yofi will talk about. But focus in our Ethyde project is explaining for domain experts, like medical experts. And there we need explanations which help to support comprehensibility of AI decision-making and to support calibrated and not naive over-generalized trust. And I think that understanding, comprehension, is really important for interactive machine learning, yeah, which has not so often discussed together, actually. But I think you can only meaningfully interact and correct an AI system if you understand at least partially how the computation of an output happened. And finally, for end users, there is also much discussion here. It's mostly about transparency of data-based decision algorithms, like getting an insurance, getting a loan, getting a proposition by a health app, and so on. So I talked already about different explanations and showed you relevance-based approaches, which here are just shown with an abstracted example from industrial quality control. And there's a small error. This square should be over this dark spot in the top. I'm sorry about that. And another way to explain is to use concept-based explanations. So especially for expert domains, it might not be only relevant to see, okay, this part was classified as a not okay part because there is a blowhole on this part, right, when it's a steel production thing or whatever. But the relevant thing would be the object is not okay because there is a blowhole, which is near the inner border of the part. So you need a much more expressive way to explain in many contexts like this, or also medicine. You can also explain with near hit and near miss examples, which is a current research focus in my team, where you show a similar instance which is also classified as not okay, and a similar instance which is classified to the other class for binary decision making here. And this helps the user to get a more global understanding of the decision boundaries of the learned model, and also is a good guidance for model adaptation. I skipped the rest. Just mention here a review Yofi and colleagues wrote about explainable AI, where there are more methods in. Okay, I skip the concept-based explanation. Just one thing. So yeah, basically you start with images, you learn, for instance, CNN classifiers, then you use information from the convolution layers of the systems and a relational background theory, maybe about spatial relations. And then you learn on top of this symbolic rules where you can describe this is a teapot because it has a handle on the one hand, and opposite this, the thing where you put the fluid out. And because I have a group of cognitive systems, we don't only develop new methods for XAI, but we also do psychological experiments to evaluate what we are doing. And for instance, we could show at a paper at a cognitive science conference that these type of relational explanations can have a positive effect not only on trust, but also on performance, both important concepts from human AI teaming. I skip the near miss and come to the explain to revise. So I hope I brought my point about that there are many possible approaches how you can realize XAI methods, and I think they are an important foundation for human in the loop approaches, for human agency and oversight, where you have explanations basically in both directions. So classically XAI goes from the system to the user. But when you take the human in the loop, the human might be able to give feedback not only on the output class, but also on the explanation. And the human could say, okay, look, this near hit example is actually also a miss. Or look, this part in a concept-based explanation is completely irrelevant, and so on. And this is also called explanatory interactive machine learning. And there is one very often cited paper by Tsaous and Kersting. You might know Christian Kersting, at least from TU Darmstadt, where they introduced an general framework of an algorithm how to do explanatory interactive machine learning, which is called CAIPI. And we use this in many different domains, for instance, for medical image classification, where you get the user feedback on near hits and near misses, and then you use this to adapt the decision boundary of the model. We use this also for culture-specific fairness adaptation, which might be another interesting topic to discuss in general. And however, current state is, as shown in a recent publication at Nature Human Behavior, this is a meta-analysis of many, many empirical studies about human AI team performance. And this paper showed that nearly for every domain, the best of humans or the best of AI, depending on the domain, outperform human AI teams. Yeah, that sounds not so good. It's a little bit disappointing, but on the other hand, it gives lots of opportunity for interesting and important research. So the reasons might be that humans over-rely on the output of AI system, but a more crucial and interesting reason, in my opinion, is that we can have a mismatch between human cognitive processes and human AI alignment. So basically, what we are doing in this symposium is to the core of cognitive science research, and we should look at this in a multidisciplinary, interdisciplinary perspective from social science, psychology, AI, and human-computer interaction. And I finish with what we currently had as an output from a Darkstuhl seminar about aligning generalization between humans and machines, where a huge team basically of machine learning researchers with some psychology researchers tried to get a better understanding how we can align the two for better decision-making support. Thank you.
So what I'm going to talk about is biases. What I usually do is machine learning, but maybe not the kind of machine learning that you think of. We have databases like this one here. We have lines. Each line is a person, and we have some observations. Like the first has primary education, is single, male, and doesn't have children, and it has a minus. That means it's a counterexample to some concept. There are also some persons with pluses. And what we then want to do is we want to predict for a new person, is it a plus or a minus? And we don't have a huge neural network where we don't know how this happens, as we just saw in Ute's talk. What we have is sets of rules. Like here, simple rule, it's a plus if the education is primary and it's low and marital status is married and so on. So that's a valid solution in principle. But if you look back, what I did here is just, I took all the pluses and converted each one of them into a rule. We haven't really learned anything. We have just memorized the examples in a way. So that's not what we want. What we want is to have something simpler, more compressed. And for doing that, we actually need something that is called a bias. We need to have some criterion that lets us find rules that are simpler than the examples. So like this one, that would be a good solution. It's very simple. It's a plus if the marital status is married. We could go back and check that holds for like 4 of these examples, doesn't hold for all of them, but it's an implication. So that's easy to understand. It generalizes. Also for new examples, you would be able to make a reasonable prediction here. And the term bias was introduced very early in machine learning. So that's a very classical paper, 1980. OK, I don't really see the pointer here. 1980, a technical report from Rutgers University from Tom Mitchell. He's one of the founding fathers of machine learning. And he says bias is necessary for making an inductive leap, for generalizing from the examples to something general. And he also illustrated this term, and he gave some examples of what you need. So he defined it. We use the term bias to refer to any basis for choosing one generalization over another. There might be different generalizations for these examples, but you pick one of them and say, this is the one I think I'm going to use. This is my set of rules that I will use for classifying new examples. And as there are many choices, you need some criterion that is not only consistency with the examples, so not only being correct on the training examples. And he gave several things, examples. The one that is usually most common in machine learning is a bias towards simplicity and generality. If you have a very simple explanation that is good, that actually helps you. There's a principle that sort of captures that is called Occam's razor in machine learning. Goes back to the 13th century. A Scottish monk, William of Ockham, he says, and I used to have the Latin phrasing somewhere, but I forgot it's there actually. Yeah, I'm blind. It's in the box. So it basically translates to entities should not be multiplied without necessity. So don't make things more complex than they are. Find a simple explanation. That's what machine learning also tries to do. Find a simple fit to the data, even to the extent that sometimes you might not want to fit one point exactly, but just be close enough so that it's good. And that is also what Ute has mentioned before, overfitting. Overfitting is when you try to fit every training example exactly. That is sometimes futile. Sometimes you want to make mistakes on the training examples because you get a better generalization. So simplicity is good. Now, what I'm worried about is I don't think simplicity is good when it comes to explanations. So here's one of my favorite cartoons. How do I get from your place to your place from Lexington? Well, simple explanation. Starting from your driveway, take every left that doesn't put you on a prime numbered highway or a street named after a president. It's a very compact thing, but for applying that, you would have to reason, and I would have maybe preferred a slightly more elaborate set of instructions, as I would have this morning, by the way, for finding this whole very complicated for me. It took me several rounds, but anyways. So that's so this bias for simplicity, I don't think that works well for explanations. It works well for learning, not so much for explanations. Another example here. So if you see that here, that's a trunk. You know what animal that is. That's an elephant. So if you see a trunk, you know the animal is an elephant. And that would be what the machine learning system learns. It would strive for simplicity and therefore learn if the animal has a trunk, it's an elephant. And that's all it knows about elephants. In this case, where we try to focus on what we call discriminative features, features that discriminate the elephant from other animals, clearly the trunk. But maybe a much better rule would be, well, if you have a trunk, if you have tusks, if you have ears, if you have thick legs, if you have gray skin, all of that, elephant. So that is also known as a characteristic rule. You have much more information in the rule here than you would actually need for predicting that it is an elephant. For that, this would be sufficient. But for understanding what an elephant looks like, for characterizing an elephant, all of that is actually much better. So another machine learning pioneer, Michalski, also in the 80s already, said that there are two different kinds of rules. Discriminative rules that go which features imply the class, and for that, trunk is sufficient. If you see trunk, it implies elephant. Characteristic rules actually go the other way around. What is implied by the class? What is implied by being an elephant? So you might also view that error, that is an implication, by the way. If elephant, then all of that. So that would be another way of viewing that. And notice, the main thing for me is, that is, of course, much more complex. It's not a simple rule. It's a complex rule. But I do think it's a better explanation. So here's another example from practical work. There's a benchmark database that is frequently used in machine learning, or used to be. It's much too simple nowadays. Mushroom database. And it contains characterizations of various mushrooms, thousands of them, with various attributes, and the classification task is predict which one of these mushrooms is edible and which one is poisonous. And you find rules, very simple rules, that work very well. Like it's poisonous if the odor is foul. It works for 2,160 mushrooms, is always correct in that database. Or it's poisonous if the odor is pungent. I don't know exactly what pungent is, but it's also a bad smell. So you take the mushroom, you smell it, and if it smells bad, better not eat it. So that's what we have learned. Now, I'm not an expert in mushrooms, but from what I remember, there are books about classifying mushrooms. It's certainly not as simple as that. Even though, as I said, these simple rules, they are really correct in that database. But if you have a different rule learning algorithm, one that uses what I call inverted heuristics, but I'm not going into the details here, you get more complex rules, like here. It's poisonous if the wheel color is white, chill spacing is close, no bruises, ring number is 1, stalk surface above the ring is silky. Also classifies 2,000 examples correctly, doesn't make any mistakes, is a much longer rule, gives us more information about that type of mushroom. Again, I don't know whether that's right or wrong, just have the evidence, as you said, evidence-based guarantee for the explanation that it usually is right. Okay. There are also some more practical things. That is from a database in coronary heart disease. I don't understand any of that actually, so to just see it's longer, but even though it's longer, which means more restrictions, it actually covers more examples. That's slightly counterintuitive, but that is because many of these features correlate with each other. You don't really need all of them. They are not all discriminative, but still, it's good to add them. One more example for brain ischemia. Discriminative rules learn very simple concepts. I don't understand any of that again. But if you use something else, you also get things where you say, okay, I know age is sort of important, cholesterol level is important, you add them, but they would be covered probably implicitly if you just add the test results that you have here. But here they are still added. So that, I would still say, is a better explanation. All right, so we need bias to learn good rules, and the bias for simplicity that is usually used is maybe not the very last thing that you want to, is maybe not the thing that you want if you want to have good and convincing explanation. So I had this Thomas Klieger, he was already mentioned on one of the slides, was a postdoc, and he pointed in my group for half a year or so, and he pointed me actually to cognitive biases. And cognitive biases, again, the term bias here, and that is something that, again, makes you choose among different things when several options are possible. In this case, it has a negative connotation. I mean, you probably know all of that. It's typically a mistake that people make. In machine learning, the bias is not so much a negative connotation. It's something that is necessary. And the idea that we are now following is that these cognitive biases might actually be helpful in understanding what is a good explanation. So cognitive biases are, of course, the conjunctive fallacy that you know, the Linda example. I'm not going into details here. What I want to talk about briefly is Thomas did this set of experiments where we presented different rules in 4 different domains. We always presented pairs of rules, and we asked users, so that was sort of a crowdsourcing experiment, mechanical Turk type experiment. So we do have a representative sample, but we don't really know exactly what it represents. There was some sort of hurdle. It wasn't everybody that could answer, but anyways. So we asked them things like, we showed them 2 different rules. If, like there was one domain in quality of living, if the country falls into all of the following groups simultaneously, it's a European Union member economies and it's imperial free cities. whatever that means, then the quality of the living is the highest. And here's a different rule. And they were asked, which one of these two rules would you prefer, or which one would you think is more plausible? And they also got the additional information. They are equally correct on the training data. So they knew there is no really one that is more accurate, but which one would you prefer as an explanation? So we asked that in 4 different domains. Like here, that's an example. Which of the rules do you find more plausible? Okay, and the first thing, that was actually my main interest, which is why I got Thomas started on that. I wanted to find out whether the length has any relevance here. And it turns out in these 4 domains, there were 2 where the length didn't really have any effect here. So there's a correlation coefficient here. And in 2 other domains, including that mushroom example that I just showed you, it had a slightly positive correlation. That means longer rules are actually better, were conceived to be more convincing than the shorter one. Which, by the way, just as I mentioned, it also happens here, right? People pick the wrong answer. Linda is a bank teller and active in the feminist movement, as opposed to the correct thing, which is just a bank teller, because that is a stronger thing. But still, people tend to prefer the longer one here. And they also tend to prefer that here. So I do have some weak evidence that shorter rules are not better understood. Even weaker, but still a slightly positive signal that longer rules might be more acceptable. That was my main interest. But Thomas also brought in these other cognitive biases, which I thought was quite interesting. And again, we drew on another former student of mine, Heiko Paulheim. He worked in a setting that he called zero-knowledge data mining, where he took some statistics like the quality of living. Where is the quality of living high? Vienna used to brag about being top 1 spot there, but it fell back recently. Anyways, and he brought in publicly available knowledge from the web and tried to learn rules on explaining why does a city have a high quality of living. Like here, a simple rule is quality of living is high if many events take place. It's a good explanation. But he also found things like quality of living is high if the number of records made in that city is greater than 1 and the number of organizations is greater than 22. Or it's a high quality of living if you have 18 bands and more than 1 airline that has been founded in 2000. The rules work, but they are not very intuitive. So what can we do about that? So one thing that is here is semantic coherence might be something that is important. So the quality of living might, or maybe let's go the other way. The number of records made or the number of bands and the number of airlines, that's not very a coherent explanation. They don't really go well together. So maybe this is something that we can use. We would prefer conditions that go well together. That's something. Another thing is relevance. Thomas actually checked for that in the survey. It was a separate part of the survey. So in the mushroom, for example, in addition to asking which rule is preferable, he asked, do you think that attribute is completely irrelevant or very relevant, cap shape, or actually a concrete condition here in the movie database? Do you think for the quality of a movie it is important that it contains an Academy Award winner and so on? And he again asked for that and found sometimes a positive correlation, but again, not all that strong a signal. But again, it's something that might at least sometimes play a role. Another thing, another famous cognitive bias is the recognition heuristic. That is the thing, if I asked you, well, it's not animated now, but because I converted it to PDF, but usually it goes like, if you see Hong Kong, if I ask you which one is the bigger city, Hong Kong or Chengdu, and you don't know that example, you might be tempted to say Hong Kong because everybody knows Hong Kong, but Chengdu is actually more than twice as big. Another classical example, which you probably all know, but usually I tell this to computer scientists. They don't know this yet, or some of them. Anyways, so again, this is something we checked. We tried to find some correlation here between, so how do you measure whether a person recognizes that? And one thing we came up with is to try to see how central is this concept in a knowledge graph. But maybe this is not, also the results here were not very strong. So this was observations. We generated rules in different ways, presented them to users, and tried to find out something about how they evaluate that. Now, what I actually want to do, what I'm currently working on, or where I have a student working on it, is to actually try to use that information in rule learning algorithms for coming up with more plausible explanations. Okay, so I'm going to skip over that. There is just many of these cognitive biases. And here is something, again, an example of Thomas, where he tried to say which effect they might have. So, for example, one cognitive bias says the first thing in a rule is perceived to be more important, whereas logically it's completely irrelevant in which order you present the conditions in a rule. But might be something to think about. The most important thing should be presented first, and there are other things. Anyway, so the final thing I want to briefly talk about is a system that my student Parisa is working on these days. She's looking at cognitively biased rule-based interpretations from explanation ensembles, short CORIFE. And the idea there is that we take rules or explanations that have been found from various systems, or typically from an ensemble. An ensemble is a way of generating many different diverse explanations. And taking that, also the data from which this has been learned, and also a knowledge graph that tries to capture some knowledge about the domain. If we take all of that, we want to have explanations that are more convincing, or that follow these principles without losing too much of accuracy. And so far we tried 3 different of these cognitive biases. One is semantic coherence. Conditions should go well together. How can you measure that? If you have a big knowledge graph here, so that is, the nodes are some entities, some knowledge that you might have, and connections are typically among things that are related. If you have one rule that combines these 3 green rules, these 3 green conditions, and implies that blue one, that's probably more convincing than one that takes here 3 different ones that are very diverse. So that might be airlines, that might be number of bands. That's not very convincing. So that's something. It sort of works. You see here the blue curve is accuracy. That is a parameter that trades off how much weight do you put on being accurate and how much weight do you put on the semantic coherence. And you see you don't lose much accuracy, but you can gain much coherence. This is the yellow curve. So it gets better in coherence while stays not quite, but almost the same in terms of accuracy. Another thing that we tried is recognition. So that might be, for example, if you have, you could model that by having some sort of function that tells you how important is each node for the user. Or a simple thing that we said, if it's up in the hierarchy and more abstract, that is more important than being down, or the other way around. So we tried both things. So here's, for example, one where we tried to get rules. They are reformulated here, but you get the idea, where you have rules for a medical doctor and a patient. If a patient presents angina, I don't know, asymptotic chest pain, ventricular ECG, and so on, several symptoms, and they are they are quite medical, these terms, as opposed to have an explanation for a patient. If you have reported chest discomfort, show signs of irregular heart activity, and the test results suggest that your heart might not be getting enough oxygen. So that's it's a more abstract explanation, and the other is more detailed explanation. And they sort of work the same on the data. Okay, I'm almost done. There is one more, and this is the conclusions, and I'm done. Thanks.
Okay, it's fine. Yeah, keep going.
Okay, well, there is one more that is semantic relevance. If you want to learn something for that, pick conditions that are closer to the concept and not those that are far away. And we also have some results, and it again shows the same thing. Accuracy stays almost the same, and we can improve according to that criteria. Yeah, and the conclusions are biases are useful for machine learning, and we should go into looking at cognitive biases as a bias for machine learning. That's at least my take, all of that. Here's the papers that I mentioned, at least those that we co-authored or I co-authored. And there's a book on inductive rule learning, but that's already 10 years old, so maybe not the most reliable source anymore. Thanks.
Okay, so welcome to my talk on perceived ability as a factor of trust in human AI teams. This is part of my dissertation, which I recently defended, so I'm really happy about that. But I will start with an introductory example here to illustrate what I'm trying to talk about here. So this is Bob. I've put the name there. Bob is trying to assemble furniture by this famous Scandinavian brand. And my question is, when we look at Bob trying his best to assemble the furniture, what do we do? What do we think about when we try to judge his ability to do so? So how do we judge Bob's ability to assemble this furniture? Do we look at what will Bob do next, as what is his next step to do to assemble this thing? And further, what information does Bob use to plan his next steps? And then finally, to come to the real topic of this symposium, would we trust Bob to assemble our furniture and invite him home to do the same thing for us? So the question here is, how do we judge Bob's ability, and how do we use this information to judge to calibrate our trust towards Bob? So I use Bob as a person here, but we can also apply the same things to, well, any agent, in my opinion. But first, I would like to talk to you about what I understand is an agent. And I use, well, this is not my definition, I use somebody else's definition. They claim that an autonomous agent is a system situated within and part of an environment that senses that environment and acts on it over time in pursuit of its own agenda and as to affect what it sees in the future. So this is a very broad definition. Many things fall under this definition. Certainly humans do, but also artificial agents, well, by definition do. Many animals would do, and in my opinion, even something like a central heating system that detects their environment and then tries to manipulate this environment would also fall under this definition of an agent. So when we add an observer here, that can then perceive the action of the agent within this environment. However, they cannot perceive what the agent perceives, and they can also not perceive the decision-making processes and the knowledge of this agent directly, at least. However, the observer can see what the agent does and then make inferences regarding the agent's hidden mental processes. Yeah, these mental processes, like their goals, their knowledge, this is the basis for many social perceptive theories, such as the theory of mind. Others call it mind reading, and there's mentalizing. So there are many different names for a very similar thing that basically inferences about someone else's mind. And finally, when we have this, this information about the mental processes of the agent, we can finally make a judgment about this agent's, well, trustworthiness and whether we should trust or trust this agent and rely on this agent or not. So we all talk about trust here, but I also found it a really good definition of what trust is in a psychological sense. I use here Meyer's definition, and he identifies 3 factors to trust. The first factor is the ability of the agent to perform the task well. The second factor is the well, the benevolence of the agent, whether it actually wants to help you or it wants to harm you. And finally, the integrity, which is more abstract in my opinion. This kind of says, does it have an ethic? Does it have ethical boundaries to how it operates, the agent? And the observer has to observe all of these 3 in order to fully trust this agent. However, for artificial agents, I mostly am interested in the ability aspect of this trust and kind of just ignore the benevolence and integrity parts, which probably are very interesting, and there are probably others that can talk to those aspects more than I can. But I will, well, talk about the ability here. Also, I want to note here that over-trust and under-trust are both very harmful for interacting, especially with artificial agents, as, well, the other talks already have noted, I guess. And, yeah, both can harm the team's performance. So how do we judge the ability of an observed agent? There are, again, 3 cues identified by others that people use to judge the expertise of others. The first are source cues, very easy to identify for everyone, just who is the person that does it and what are the attributes of the agent, like titles, physical appearance are frequently used, but also age are interesting aspects here. For example, is Bob a carpenter? Then you could use this information to already come to a conclusion about their expertise. There are surface cues of their behavior. So how do they perform it? Do they do it confidently with a smile, or are they like insecure and shaking a bit? These are surface cues, also very easily to interpret. But yeah. Finally, there are semantic cues, and this is the actual decision-making processes and the decisions the agent does. So what do they actually do? And in my opinion, these are more difficult to interpret to an observer because they also need domain knowledge to actually interpret what the agent is doing as to take that as an information about their ability. Yeah, exactly. The first 2 ones are, they can be manipulated, and the agent can act confidently without any knowledge, and the agent can, well, look taller and try to imitate a title online, for example. So these can be manipulated in order to, well, evoke trust in others. However, the semantic cues, the information of what someone actually does or says, is not easily manipulated, since manipulation of these comes with an actual decline in performance. So I have done some work on using this framework I just explained to you. It's recently published, so I'm also very happy about that. And I claim that performance, rather than the reputation about an agent, affects the human's trust towards this agent. And I will show you some results I present in this paper. So it's an online experiment. We gave a training about, well, this game to all of the participants. Then we said you will soon play together with an artificial agent. And this agent is either very well high performing, like machine learning, trained on years and years of experience and so on, or it's a low reputation agent, it's a student project, beta version, and well, keywords like this were used there. Immediately following this reputation manipulation, we used a trust questionnaire, self-report questionnaire for the participants. And after this questionnaire, they then actually interacted with this agent on this game. This interaction looks like, well, many of you will know Tetris, so I will not really explain how Tetris works, but this game was slightly altered to be a more cooperative game, where the participant can choose one of these 4 pieces that are shown in the box above, or it can delegate this task to a computer, to this artificial agent. And then the participant has to place this piece that is either chosen by them or by the computer. They have to place this in the Tetris rules game set. And we use this delegation to the agent as a behavioral measure for trust, which is debatable, but we can talk about this later. So we have basically 2 measures of trust here. And finally, we do this self-reported trust again. So we have 2 measures of trust, the self-reported trust and the behavioral trust. And I will show you the results of each individually. So regarding the self-report trust, we have well, in my opinion, very interesting interaction effect. Oh, I can better use this one. So before the direct interaction with the agent, the judgments were only based on the reputation of this agent. And we can see that the self-reported trust is only dependent on this reputation. So the lighter boxes here are for high reputable agents, and the darker boxes here are for lower reputable agents. Very understandably, since they have no interaction yet, no first-hand experience of this agent. But then after experiencing this agent firsthand, we basically see no effect of reputation anymore, and all of the difference are based on the actual experienced performance of this agent. And we can see then this development over time in the behavioral measure, where we can see here we can see the delegation decision percentage over time. And we can see that the delegation decisions are very similar for all conditions in the beginning, but then very quickly decline in the the low performance group, and they then come to a kind of stable area after about 25 trials. On the other hand, the high-performing group, they start high and they also continue to delegate to this agent, to the high-performing agent. What we cannot see here is an effect of the reputation. Neither an interaction effect with time nor a main effect of reputation. We believe that this might be because the delegation is not a direct translation of trust. There are other factors that play into whether I should delegate to this agent or not, such as the novelty of the agent kind of evokes a curiosity-driven and exploration-driven approach, and the participants probably just want to see how this agent performs and how it works. But then after getting some very frustrating results, they decide to no longer delegate as much. On the other hand, when it works well, they continue. So this might be the reason why the behavioral and the self-reported measures, they kind of diverge here regarding the reputation. Further, I'm also very interested in the role of the participants or the observers' knowledge regarding the task. And I have some information also in this experiment. However, these are very exploratory results, so I kind of said that before, because all of the participants here received a training, so we have no experimental difference between the participants. However, they bring some natural fluctuations, and we can use those. So what is the role of the participants' performance in their post-interaction self-reported trust? We can see that for high performance, for the high performance agent, the participants' own performance doesn't really have any impact. But for the low performing agent, we can see that the post-interaction trust for badly performing participants is way higher than they deserve. And when the participant is better at the game themselves, they can identify the badly performing agent and appropriately punishes their bad behavior in their trust. So in order to accurately calibrate their trust towards this agent, the participants have to have knowledge of the game themselves. Otherwise, they just kind of follow the reputation or whatever. They use whatever information they can, but they cannot use this information about the agent's actions. Further, the participant solo performance also has some impact on the team's performance. This is not very surprising, but I have it here nonetheless, black on white. So to discuss these results, the main take-home message here is the perception of expert performance does increase trust. So it's not super surprising, but it's kind of reassuring to know that. And I have shown this through the self-reported data, where initial trust is linked to the agent's reputation, but then gets overridden by the direct interaction. However, the delegation decisions, they were not directly influenced by the reputation, and we think that this might be due to the novelty and the curiosity of the participants. Finally, the agent performance had significant and large effects on the delegation decisions, which, well, as I discussed, the delegation decisions are, I think, an appropriate measure of trust, given that other context behavior is controlled for. And yeah, I have some exploratory results on the observer expertise. However, I have more dedicated experiments for this observer expertise, which I can show you now. However, I think the time is getting... I have 2 minutes. I think I will just skip over those. And thank you for your attention.
Okay.
Yeah, I have the honor to give the last presentation in the symposium. So I'm a behavioral scientist, so I will guide you through some empirical studies on judgment and decision making. Here, trust, that's why it's probably a little bit different than the talk before. Trust is only defined as a behavioral measure. So it's, another term would be reliance probably. Yeah, how much does some advice that participants receive, whether it's from another human or from an artificial agent, how much does it actually affect their judgment and decision making? Yeah. And as Ute already mentioned, yeah, we have different forms, or the level of trust in AI systems varies a lot among users of AI systems. Yeah, we have cases where there's distrust in AI output, when people are skeptical about the AI system, and we have cases when they over-trust or over-rely the output, and then there's this idea that there is some some level of trust that is well calibrated wherever this is. I put it in the middle, and then but it's not suggestive that there is a certain range of distrust and a certain range of overtrust, and then there in the middle is calibrated trust. I'm not suggesting that. It's just that there is distrust, there's overtrust, and the difficulty is that a priori in a certain use case, in a certain situation, for a certain AI system, it's very difficult to predict actually whether we will have a case of distrust or overtrust. That's actually a difficult thing to predict. And you also find these in these ethical guidelines that both forms of trust are discussed in both perspectives. We have these, Ute already mentioned, the trustworthiness as a prerequisite for people and societies to use AI systems. Yeah, and here it's a little bit that we are skeptical. We are probably skeptical about, or the user is probably skeptical about AI systems, and we need to assure that with some principles that actually users can gain trust in AI systems. Yeah, that we start from the left side of this line. And then, but also there in these ethics guidelines, you find cases when they discuss the fear or the risk that actually people may blindly follow AI output, and that the AI system, which is actually only designed as a decision support, might become the secret decision maker, right? And so, and as a designer of an AI system, it's difficult a priori to say, okay, where am I? What will be the problem? Will it be a problem of distrust or overtrust in my specific case? And in our research that I will show you, it seems that one simple rule might be that the decision context matters, whether we are on the left or the right side. Okay? So in this decision-making context, I actually here show you examples of two different contexts. One is a moral context when people make ethical decisions, and the other one is what we call epistemic context, when there is a ground truth, when there's a right or wrong to a question. Okay? And I will start with a few studies in the moral domain. Yeah? So actually here's one study that we conducted in December 2022, so a few weeks after ChatGPT was first released. And here you see actually two famous dilemmas, ethical dilemmas in philosophy, the trolley problem. Yeah, so the switch dilemma is that's the original trolley problem, where a trolley is heading towards 5 people, and these 5 people will be killed, and these 5 people can only be saved if the trolley is diverted to a side track where there's one person, and the question is, should this person there pull the lever to divert the trolley towards this one person? And then there are many different versions of the trolley problem, and one is what's nowadays called a bridge problem. Previously, it was called the fat man, but there's one, but it's not politically correct anymore. So instead of a fat man, there is a large person with a backpack standing on a bridge, and the trolley is heading towards these 5 people, and this trolley can be stopped when this large person with a backpack is thrown off the bridge, and then this stops the trolley, but the person is killed in this process. And we know actually that in the switch dilemma, most people think that the lever should be pulled, so the trolley should be diverted, but most people in the bridge dilemma think this person should not be pushed off the bridge, right? So, and after ChatGPT was released, we also asked ChatGPT, what should we do here? And we realized quite quickly that ChatGPT actually gave different answers. It was almost a coin flip. So sometimes it says, well, you should sacrifice this one person, and other times it said you should not sacrifice this one person. Yeah? And so what we were interested in, okay, does this actually affect people's moral judgments? Yeah? So we asked ChatGPT, screenshotted the answers of ChatGPT, and then gave people these transcripts, and then asked them to what do they think should be done in these trolley problems. Yeah? So here the experimental procedure. Yeah, so we confronted them with the 2 trolley problems. Each participant only saw one, so either the bridge or the switch dilemma, and then we also gave them one of these transcripts where ChatGPT either advised in favor of sacrificing one person or against sacrificing one person. Yeah, and in some participants, we told actually that this transcript was from ChatGPT, a chatbot. So back then, we explained to them what ChatGPT actually is, and some others we only told them that it comes from a moral advisor. Yeah. And what we see here is, you see what is plotted here is the proportion of people who actually said that this one person should be sacrificed. And on the left side, it's for the bridge dilemma, on the right side for the switch dilemma. And then dark gray means they received advice that this one person should be sacrificed, and light gray means the advice was should not sacrifice one person. And as you see, this transcript from ChatGPT actually substantially influenced their moral judgments, right? Especially in the bridge dilemma, even switched the majority opinion. And so obviously these transcripts influence their judgments, but what is even more worrisome is that afterwards we asked them, okay, what would you have said if you wouldn't have read the transcript? And what we see here that actually most people said, I would have said exactly the same thing. Yeah, and then, but here what is plotted is, again, in the experimental conditions. So they said, so that they took over this random ethical stance of ChatGPT and thought it was their own, right? That's kind of worrisome. Yeah. So this influence was subconscious. Yeah. And we also had other studies, which I only go through briefly, actually prior to ChatGPT, where we tested how algorithms or artificial agents can affect people's moral judgments. Here's this study 2 was a vignette experiment, so it's a hypothetical decision making, just like the trolley problem, obviously, where participants are described a certain decision situation, and we asked them then, what do you think you would do in such a situation? Yeah, we had different contexts, and they were less stark than the trolley problem. In the recruitment, health, or law. So for instance, imagine you're a recruiter in a company, and you have a position to fill, and you have 2 applicants. One is a friend of yours, the other is a stranger. The stranger is more eligible. Who would you give the job, right? And then they received advice either from a human advisor or from some kind of algorithm that we explained to them a little bit, and then this advice was you should or you should not give the position to your friend. Yeah? And what we found actually that this algorithm, or when we describe the situation that the advice comes from an algorithm, it influenced their judgments just as when the advice comes from a human. And then we try to stepwise actually make this algorithm more questionable. So then in the next experiment, we told them that so in the first experiment, told them that the algorithm is trained on the data, on the decision-making of human experts. Then in another situation, we explained to them that the algorithm, we told them explicitly that it's completely unknown what the algorithm is trained on, but it still affected their decision-making or their judgment. And in the third situation, then we told them actually that the algorithm is trained on the judgments of convicted criminals, and it still affected their judgments, even though if we told them directly this advice comes from a convicted criminal, they ignore the advice. But if we told them that it's from an algorithm that is trained on the judgment of convicted criminals, they took it into account for some reason. Yeah. So this advice obviously influenced their judgment, and it was actually even then when we made this algorithm as questionable as it gets, right? And then in the third study, this was a behavioral experiment, so it was not hypothetical decision making. We did an experiment with 300 participants. They played a dictator game. It's a famous game in psychology and economics. The dictator game is actually an allocation task, so it's a game of between two people. And one person receives an endowment, let's say, of 10 euros, and this one person can then decide how to allocate these 10 euros between me and this other person, right? And this other person has nothing to say about it, so it just can accept whatever I do. So that's why it's called a dictator game. And so this is used to measure generosity under certain conditions. And also here in this experiment, we saw that actually when they are advised by an algorithm, it was very easy actually to lower or increase their generosity. Right? So what we see actually, or what I hope to have conveyed in these studies, that actually in a moral context, people rely overly strongly on AI-based advice, and even in cases when we actually tried to lower trustworthiness, when we made the algorithm questionable. Right? So here we are on the right side of this figure. So we have overtrust, over-reliance. And then we did a series of studies in an epistemic context. So we used actually image-based classifications. Yeah, this is so we came from medical decision-making, where AI assistance systems might be used to classify tumor scans or whatever, and we wanted to actually see how we can design the interaction between human and such an AI system that the human makes responsible decisions. Right? So, but the problem for behavioral scientists is that these tasks, these image-based classifications, are typically very specialized tasks, right? And to get study subjects, you need subjects with domain knowledge, which is very difficult. So that's why actually we took a lot of effort to develop a workhorse that we used in our experiments, and this was actually the classification of cats, right? So this is what we had in mind. So there's some kind of classification task, but obviously this is not what we can use with lay people, right? So, but what is a characteristic of these classification tasks, that actually if there is, if a picture is, or if an image is misclassified, it's typically misclassified between two neighboring classes, but very seldomly across several classes, right? So, so a task where we thought that lay people bring some kind of knowledge and which has the same characteristics is that if they have to classify cats into domestic cats, small cats that are not domestic, or big cats. And we had 90 cat pictures that we actually, in several pilot studies, participants classified these pictures without any help, and we found exactly that. So if there was so most of the pictures were classified correctly, but if there was a mistake, then it was between neighboring classes, but not across. And we also had a nice range of difficult images. So some images were very easy for people to classify, others were very difficult. Okay? So, and what we by now have done is actually we had run many experiments. We collected much more than 100,000 classifications of more than 5,000 participants in several treatment variations. Okay, and each procedure or each experiment was actually the same. So each participant always classified 20 randomly selected cat images, and we used performance-based pay, so all experiments were incentivized. So the better they classified the pictures, the more they earn, right? And we always use the between subjects design. This means that each subject was only, or took part in the experiment in only one experimental condition, right? Yeah, okay. And here's, I mean, we produced a lot of results. I guide you through some main results, okay? So, and here's one main result. So what you see here, what is plotted is, so each dot is a cat picture, is a cat image, and it's the proportion of correct, how many participants classified this picture correctly. And the horizontal axis, the difficulty of images actually from our pilot data. So for each picture, we know from our pilot data when we developed the workcourse how difficult it was for people who are not advised by anything, how difficult it is for them to classify the picture. So difficulty means, a difficulty of 1 would mean that none of the participants would have classified this picture correctly in the pilot data. So, but what we see here, so and then this is a figure where we had 3 treatments. So the black line is when participants had there was no advice. And these other 2 lines, which are actually indistinguishable, is when the advice came from another human being, it was a human expert, or an AI advice, The advice was always, the advisor, whoever it was, human or AI, always said, this is a domestic cat, or this is a big cat. This was the advice, right? And we made sure that the performance of our human experts and the AI was the same across experimental conditions, okay? So, but what you see here is that actually, as these pictures, the difficulty of these images becomes larger, then actually the performance decreases also when they have advice, but the advice helps a little bit. It increases their performance when they receive advice, no matter whether it was advice from a human or an AI. It increases performance by 10 to 15%, but actually there is a lot of performance gain possible. And these difficult range of images, if they would blindly follow the human advice, they could almost double their performance. If they blindly follow the AI advice, they could almost triple their performance in this range, right? So here's actually a very similar picture, but now it's not the performance or the accuracy of each image, but it's whether they follow the advice, whether their classification is in line with the advice that they receive. And what we see here actually is that the more difficult the picture is, the lower the likelihood that they follow the advice that they receive. And dark gray or black is when they receive advice of another human being. Light gray is from an AI, and you see that actually when they receive advice from an AI, then actually they discount this advice even more. And we have some images. We have some images where actually both agents give exactly the same advice. For some of the images, of course, humans give another advice, human experts give another advice than the AI, but we have some images where actually the advice is exactly the same. And here, even for these pictures, we see that the AI is discounted even more than the human. So we have evidence of egocentric discounting. It's a term from psychology. So it means that you discount the advice that you receive and you put too much weight on your own intuition, especially for difficult cases, and additional distrust we see with AI advice. Sorry. And then actually our difficulty was, so these results are extremely robust against several experimental manipulations that we tried. We tried to convey different statistic information about the performance of other subjects, about the performance of the AI, so we really tried many different things. Still, they always discounted the advice, especially for difficult cases. And we also implemented some conditions where they actually had time to learn how to interact with the AI, where they receive feedback and learning tasks, where they also classified cat pictures, and when they learned actually that the AI is much better than they are themselves, but they were still not willing to trust the AI a little more. And one difficulty, I think this is also a nice finding. One issue is that participants have a difficulty to recognize difficult cases, actually. Yeah? We see this when we plot decision time. So here it's, again, the difficulty of the images, and then it's the average decision time that they take to classify such an image. And decision time or classification time increases at first with the difficulty of image, and then it decreases again, right? And this led us for another actually experiment where we, before they classified the image, we asked them, please rate the difficulty of the image for you to classify. And we see the same thing. Yeah, their rating, so their subjective, but their perception of the difficulty increases at first with the actual difficulty, but then actually it decreases. So one difficulty is that people or humans have a difficulty in identifying difficult cases. Okay? Nonetheless, the negative part is that in one treatment we even told them, by the way, this is a difficult image, and in difficult images the eye has a very high comparative advantage compared to your performance, and then yeah, so they still didn't take the advice. Okay, so the main conclusion, I have to end. The main conclusion is that in these epistemic tasks, actually, we are on the other side of the calibrated trust in our experiments. So we are on the side of distrust in AI, and it seems to be very difficult actually to increase trust. And so these dots are our studies that I put there. So in epistemic context, it seems to be a case of distrust. More context seems to be a case of trust. Yeah, but of course, this is ongoing process. So this is our decision rule right now. But there are also cases where actually both are combined. So the doctor actually solves an epistemic task which has ethical implications on a third person, namely the patient. So the question is, where will such a decision task actually locate in this picture? So thank you very much. And then, yeah. The very last point is only that maybe we should, and this is just a little bit provocative, Ute, maybe ethicists should think about, wouldn't it be okay at some future point in time if AI outperforms human performance, and if we are not able, we computer scientists and social scientists, to increase trust, should we think about situations when it would be okay to get the expert out of the loop? But yeah.